Good. Let me introduce our next speaker, Manuell, and his talk on a two-dimensional bifunctor theory.
Thank you. I would just like to start by thanking the organizers for organizing the conference, and also mention that this is based on joint work with Peter Fall and Jose Sequeira. So the starting point of kind of this talk is this classical theorem, the bifunctor theorem, which actually appears, it's the first proven results in categories for the working mathematician. So this is the starting point. And the idea is it tells you kind of when you can construct a bifunctor, that's a functor from a product category, given kind of families of functors. So suppose we have two families of functors. So one goes from one of like the families goes from category B to a category D, and another one goes from C to D. And then the first family is indexed by objects of the second category, and the second one's indexed by objects of the first. And they satisfy this compatibility condition on objects. And then the theorem states that we have a bifunctor that essentially restricts on each component to give you the original families back. So when you substitute in C, then we get our LCs and so on. And it tells you that you can do this if and only if essentially it commutes with respect to first applying the first set of functors to the one input and then the second one, or doing it the other way around. So it's easy to see that this will in fact hold if it did come from a bifunctor. But the theorem says that if this holds, then in fact it does come from one. And the definition is just exactly what you would expect. We define it on objects in the obvious way. And on morphisms, we have two choices, but we've just assumed that both choices are equal. So we could take either one. So that's the result. It's a very simple theorem, but it does end up being useful in some cases. And in fact, what we needed to do is we were trying to prove something, and we needed a result like this, but we needed it one category higher. Sorry, like one level higher. So here, B, C, and D are not categories, but there are two categories. And rather than having families of functors, we needed families of pseudo-functors. And then they satisfy similar conditions. And as you might guess, instead of requiring an equality, as we did before on the morphisms, now we're going to require that there is some invertible two-morphism between them. In fact, a family of these for each kind of for each one morphisms you might put in. And these will then need to satisfy certain coherence conditions, which I will talk about soon. But then we can go and prove a theorem which looks very similar. So then we can prove that there is in fact a pseudo bifunctor, which restricts to give these. And furthermore, we have a converse which says that every pseudo bifunctor will kind of come from families of this form for some essentially unique choice in some sense. So this is the result that we wanted, and I'll tell you a little bit about how it's proved soon. But when we're proving this, we noticed that actually there were some similarities to kind of other concepts in category theory. And to make these clear, it made sense to generalize this construction to lax functors. So instead of working with pseudo-functors, we just do everything with lax functors. And let me just recall what a lax functor is. So the idea behind a lax functor is if you have two categories, a lax functor is going to tell you, okay, it's going to send objects of the one to objects of the other one. That's straightforward. Then it's going to be functorial on the Hom categories. So it will preserve kind of composition of the two morphisms strictly in the obvious way. But then for composition of the one morphisms, it's not necessarily going to compose them, and it's not even going to compose them up to isomorphism necessarily. But instead, all we're going to do is we're going to get a two morphism from the composite of the functors applied to the things and the functor of the composites. So we call this map the compositor, and we'll have one of them for every pair of composable one morphisms. And then similarly, we're going to have a unitor, which will kind of show that it kind of replaces preservation of the unit. So a pseudo functor is just a lax functor where these unitors and compositors actually are invertible, but in a lax functor, we don't require any invertibility conditions. So this is at least the data of a lax functor, but they're going to need to satisfy certain coherence conditions. So here I've expressed the coherence conditions in terms of string diagrams. And so this is a string diagram in the 2 category, but I'm not labeling the regions which correspond to objects that hopefully you can understand from context. And for the string diagrams in this talk, we're going to read them from bottom to top. So that will be the vertical composition, and from left to right. So this first condition here is kind of like a neutrality condition. So if we have these 2 cells, alpha and beta, we can either apply the functors essentially before the compositor or afterwards. Then the second condition is going to be an associativity type condition on the compositors. And finally, there's going to be a condition relating the compositors and the unitors, which means they act like units. These conditions might remind you of the axioms of a monad, and this isn't a coincidence, and we'll talk more about this soon. Okay, so now let's rephrase the results for a third time. So now we have lax functors. And now we're no longer going to require that these maps sigma are isomorphisms. They can just be arbitrary 2 morphisms. And again, on coherence, under certain kind of coherence conditions, which I'll get to soon, we will be able to construct a lax bifunctor from the product category. And just to kind of fix terminology, let's call this construction of turning these families of functors into a bifunctor, a lax bifunctor, we'll call this process collation. Okay, so we define it in the obvious way. So on objects, we do the obvious thing. This is exactly like the one-dimensional case. And on morphisms, again, like in the one-dimensional case, we're just going to compose. We need to pick some direction. So we just define them on one morphisms like this. And then it's fairly clear what to do with the 2 morphisms. But now this isn't all the data. We also need to say what we're doing with the unitors and what we're doing with the compositors. So for the unitors, it's straightforward. We're just going to take the horizontal composition of the 2 unitors we start with. But for the compositor, slightly more complicated. In this case, it involves the map sigma. Don't worry too much about this definition or try to understand it, because we will represent this in terms of string diagrams, and then it should hopefully become simpler. So here's a string diagram representing the form of the compositor. And here just we kind of using a convention where if a wire in the string diagram has is kind of a one morphism that we've applied L to, I'm going to draw it in red. And if it's something I've applied one of the M functors to, I'm going to draw it in blue. And then the map sigma go essentially from one composition of L and M to the reverse one. So we can depict this as a wire crossing another wire. And then the red dot and the blue dot are just the compositors. So this is how we're going to define this. Again, if anyone's familiar with distributive laws, this might be starting to look quite familiar. But so we want conditions for this to actually be a lax functor. So I've told you how to define all the data. But the question is, what conditions do we need to ensure that this actually does give us a lax functor? So again, these conditions are best represented in terms of string diagrams. And they kind of have these intuitive conditions where you have a kind of a red wire passing on top of kind of a blue wire, and then there's the compositor, and you can just shift it above the compositor. You can just pull the wire upwards. And then there are the dual conditions where you have the blue wire crossing over, and you can just pull it upwards past the compositor. So this is the first set of conditions, the ones involving the compositor. Then we're going to have another pair of conditions involving the uniters, very similar. And finally, we're going to have some kind of neutrality type condition, which says that if we apply the functors to some 2-cell, we can also move this past this crossing. So we've essentially got these 6 conditions or 6 families of conditions. And if all of these hold, then the result will actually be a lax bifunctor. Okay, so now we can try and do this construction in the case of the pseudofunctors. So in the pseudofunctors, we started with pseudofunctors, and we assume that these map sigma are isomorphisms. And in this case, it's not hard to see that the result you get back when you do this construction is actually a pseudofunctor. Then you can also go backwards. You can also go in the reverse direction for the pseudofunctor. This isn't true in general for lax functors. So this needs to be proven separately, but that's something you can do. But the main construction is, of course, this result, which also works for lax functors. So this kind of gives the original result we were looking for. But this isn't the only application that we can get for this. So there's also another example that I've kind of been hinting about throughout the talk. And that is this example of monads. So you might be familiar with the result that says a monad is just a lax functor from the terminal 2 category. So the terminal 2 category will just have a single object, and then it'll have the identity 1 morphism and the identity 2 morphism on that, and nothing else. And when we specify a lax functor, we essentially need to send the object to some object. We need to send the 1 morphism to some 1 morphism, so the identity to some 1 morphism, but that 1 morphism won't necessarily have to be the identity. But it'll need to satisfy some conditions, and the compositor and the uniter will give you the multiplication and the unit of your monad. So now let's see what we get in this case. So suppose we start with some monads. So in this case, we aren't going to have a family of functors because we're just going to have a single object. So we'll just have a single functor in each case. So these will be the kind of functors underlying 2 monads. And the condition, that kind of compatibility condition on the objects, says that the monads must be on the same object in the category. And there will be a single 2 morphism that goes from the one composite to the other one. And now this is very much looking like a distributive law. And indeed, our conditions, which I called D1, take the product of it with itself, we're just going to get the same thing back. Okay, sure. Hello? Yes, hello? Okay, sure. Where should I? Yeah, okay, I'll start at the top, I guess. So I was just explaining that monads can be thought of as lax functors from the terminal category. And in this case, let's see what our construction gives. So we're going to have, if we apply our, and now we won't have families anymore, we're just going to have a single kind of functor L and a single 2 functor M, or lax functor rather. And then these will, if we apply these to the identity, these will give us the underlying functors of our monad. And the compatibility condition will mean that these must be monads on the same object. And then we have this map sigma between them. And this is now starting to look very much like a distributive law. And indeed, the first 4 conditions are precisely what it means to be a distributive law. And the final 2 conditions are going to be automatic in this case because they involve the 2 morphisms, but we only have the identity 2 morphism. And when we apply our construction, because the product of the terminal category with itself is again the terminal 2 category, this gives us another monad back. And indeed, this monad is precisely going to just be the kind of composite monad from this distributive law. So in other words, this construction recovers the construction of a composite monad from a distributive law as a special case. Okay, and now one last application, and that's for braidings of a monoidal category. So if we have a monoidal category, we can think of it as a one-object bicategory. Now, I stated the result before for 2 categories, but it works equally well for bicategories. So in this case, we can say, suppose that all of our categories, B, C, and D, are all kind of bicategories corresponding to this monoidal category. So in this case, the horizontal composition is going to be the tensor product of the original monoidal category. And we're again just going to have a single pair of functors, and we'll just take them to be the identity functor. And then our map is just going to be from the kind of one direction of tensoring to the other one. Okay. Now the final conditions, the neutrality conditions, are just going to say that this family of map sigma is actually natural in X and Y. So it's a natural transformation. Then the first 2 conditions, the interaction with the compositors, this is going to amount to the fact that this is actually going to be a braiding. This is the usual definition of a braiding on a monoidal category. And then we have 2 final conditions, which are the interaction with the units. But I should have mentioned this before, but in the pseudo-functor theorem, those 2 conditions follow from the other conditions. So when everything's invertible, you can deduce these 2 conditions from the other ones. So this follows automatically. So this recovers the notion of a braiding in this case. And now what does our result give? So in the end, this is going to give us a bifunctor from essentially these bicategories, these one-object bicategories, the product. And what this corresponds to in terms of monoidal categories is we get a strong monoidal functor. And it's a strong monoidal functor whose underlying functor is just tensor product. And our theorem for pseudo-functors shows us that actually we can go backwards. So this shows that there's this correspondence between the braidings on a monoidal category and between strong monoidal structures on the tensor product. And this is a known result, but it is nice, again, that we recover this as a special case of our construction. So in particular, we know we get that a monoidal category admits a braiding if and only if the tensor product admits the structure of a strong monoidal functor. Okay, good. So these are our 3 examples. We actually have some other examples, but it's less clear maybe how important they are. But I just want to end by saying something about how we can think of this process of collation. And inspired by the monad case, we're going to give this data, these families of functors and these map sigma. This data we'll call distributive laws of lax functors. And now, inspired by the case of monads, we might think, okay, well, what's happening for monads with distributive laws? And well, it turns out that in the case of a monad, a distributive law, if you have a 2 category, you can construct a 2 category of monads on that 2 category. And the monads in this category are going to be distributive laws. So if we write this in terms of lax functors, we can just write this as this iterated kind of function space type construction. So here lax is going to give a category of lax functors. The objects are lax functors. And just to make things nice, I'm actually assuming that the 1 morphisms are op-lax transformations, and then the 2 morphisms are going to be modifications. So this is how it looks like if we rewrite it. But indeed, it turns out for distributive laws of lax functors, we can generalize this result. So they will correspond to this iterated construction where we've replaced the ones with our categories B and C. And now these are the objects. So the objects are the distributive laws. And now we might ask, what are the morphisms in this category? What do they correspond to? So if the objects correspond to families of lax functors, the morphisms are going to correspond to families of op-lax transformations between these. And they will need to satisfy a certain compatibility condition. And that compatibility condition essentially is the Yang-Baxter equation. So again, it has a very nice diagrammatic form. And then you can also do the same story with the two morphisms, but similar things happen. But the point of this whole process is this notion of collation. What it gives is it gives a two functor from this iterated kind of functor category to the lax functor category on the product. So we get a two functor from the one to the other. And now this is maybe starting to look, again, not so surprising, because in the case of pseudo-functors, if we restrict to pseudo-functors, then this will not only be a functor, it will be an equivalence. And this will in fact reduce to that equivalence, this equivalence essentially being the product exponential adjunction. But in the case of lax functors, it doesn't have an inverse in general. Well, there's no inverse. And but yes, it restricts to this equivalence. So this direction is essentially we can uncurry maps. So if we have a map that takes in an input and then gives a function out, we can uncurry it to give a map on kind of two inputs, but we can't go backwards. But so it's kind of interesting that we can now see all of these results like Braidings and also distributive laws of monads as kind of an instance of this kind of uncurrying process, as like a generalized uncurrying. So that's all I had to say. And you can find more details on the archive. Thanks.
Oh, there are several online. Hold on.
Lax functors also recover enrichment in bicategories.
Yes.
Have you already looked also at what your bifunctor theorem produces in this case?
Well, I have looked briefly. I haven't proved any results about it, but I can tell you. So it's already known, I think, that if you enrich in a braided monoidal category, then this gives a tensor product of the enriched categories. So essentially what it does is it takes the product on the set of objects, and it will then give you some kind of, again, the enriched category back. And this essentially generalizes that result. So if your category isn't braided, this gives like a local braiding, and this will give a way to kind of construct some kind of product, tensor product of your enriched categories. I don't necessarily know like any interesting examples of this, but that is what happens in that case.
Thank you.
Alex, you have another question? We can hear you.
Hi, thank you very much for the interesting talk. I'm reminded quite a lot of a paper of Branko Nikolic in TAC called, or maybe you already know it, the strictification tensor product or something. I just wanted to mention it in case you weren't aware of it already.
Yes, thank you. Yes, no, so that is cited in our paper. Yes, there are definite similarities. Yes, so part of these results can be understood in those terms, especially the final part in terms of the uncurrying. The distributive law kind of interpretation, I guess, is mainly what's new in this approach.
Paul, you had a question. Maybe you can write it down. We don't hear you very well.
I was just so the initial idea was the interchange law, and which is something that doesn't happen in the gray tensor product. So I wonder whether if you substitute gray tensors for all of your products, your tensor products, whether the theory disappears, that is what your theory is, or whether there's something more complicated. Sorry, I'm not a high dimensional category, so it's not a very
I guess I'm not either, so I don't know the answer to your question, unfortunately. But yeah, I guess that would be something to consider. Thanks.
Any other questions?
So thank you for your talk. What was extremely nice, I think, was your interpretation of braidings on a monoidal category. Does this approach also lead to a new approach of the so-called center construction, where a monoidal category, the center construction sends to a braided monoidal category?
I must admit that I'm not actually familiar with. Sorry. Yes. So center.
The dream
yes.
construction.
I don't know the answer to the question. I haven't thought about it at all. But that's interesting. I'll think about it. Thank you.
Okay.
It's good to have so many questions. Is there another one? What about online? Well, then let's thank the speaker again.